The morning of April 12, 1945, at Royal Air Force Worthy Down in Hampshire, England, test pilot Jeffrey Quill walked across the tarmac toward a Spitfire that looked wrong. The propeller assembly jutting from the nose appeared too thick, too complex, as if someone had grafted two aircraft together at the spinner. Ground crews stood in small clusters, watching him approach the modified Mark 21 with expressions that mixed curiosity and skepticism. One mechanic had called it Smith's folly. Another had been more direct. That contra-rotating business will tear itself apart before you reach 5,000 feet. Quill had flown Spitfires since 1936, when the prototype had barely proven it could stay airborne. He had survived the Battle of Britain, tested every major variant Supermarine had produced, and pushed these aircraft to limits their designers had never intended. He knew what a Spitfire should feel like from the moment the wheels left the ratee and ground. This aircraft, with its paired propellers rotating in opposite directions on concentric shafts driven by a 2,000 horsepower Rolls-Royce Griffon engine, was supposed to be faster, more stable, and more responsive than any single propeller fighter ever built. The engineering team under Joe Smith, Supermarine's chief designer since R.J. Mitchell's death in 1937, had spent 18 months developing the contra-rotating propeller system specifically to solve problems that had plagued high-powered fighters since the beginning of the war. But standing on the tarmac that April morning, looking at the unconventional propeller assembly, Quill could not shake a fundamental question that would define this aircraft's entire existence. Could superior engineering actually be too complex for war? CTA. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Spitfire had been the symbol of British resistance since 1940. Its elliptical wings and clean lines had become as recognisable as Churchill's voice on the BBC. But by 1944, the war had changed. The aircraft that had dominated the skies over southern England during the darkest days of the Battle of Britain now struggled to keep pace with the demands of offensive operations over occupied Europe. German fighters had grown faster, more heavily armed, and more dangerous. The Focke-Wulf 190D could reach 440 miles per hour in level flight. The Messerschmitt 162 jet fighter, though rare and mechanically troublesome, could exceed 500 miles per hour. Allied planners needed every advantage they could extract from their existing airframe designs while new jet aircraft remained in development. The solution, Smith's engineering team believed, lay not in abandoning the Spitfire's proven design, but in addressing the fundamental limitation that had constrained every single-engine fighter since the Wright brothers, propeller torque. Every aircraft with a single propeller experienced a rotating force that tried to roll the aircraft in the opposite direction of the propeller's rotation. Pilots compensated constantly, applying rudder and aileron trim to counteract these forces. At high power settings during takeoff or in combat maneuvers, the torque effect became so pronounced that it could flip an aircraft onto its back if the pilot made even a momentary error. The more powerful the engine, the worse the problem became. The Griffon engine in the latest Spitfire variants produced torque forces that made the aircraft genuinely dangerous for inexperienced pilots. Contra-rotating propellers offered an elegant theoretical solution. Two propellers rotating in opposite directions would cancel out each other's torque, eliminating the rolling tendency and allowing the aircraft to fly straight and level without constant pilot correction. The concept was not new. Auguste Rateau in France had patented a contra-rotating propeller design in 1913. Several experimental aircraft in the 1920s and 30s had tested the principle with mixed results, but no one had successfully integrated a contra-rotating system into a high-performance fighter aircraft operating under combat conditions. The path to Quill's test flight began not with inspiration, but with frustration. By the summer of 1943, Supermarine's design team faced a problem that threatened to make their most successful aircraft obsolete. The Spitfire Mark 9, powered by the Merlin 61 engine producing 1,560 horsepower, represented the peak of what the airframe could handle with conventional propeller arrangements. Engineers had pushed the design through constant refinement since 1936, improving nearly every system, but they were approaching hard limits imposed by physics and metallurgy. Joe Smith understood these constraints intimately. He had worked alongside R.J. Mitchell during the Spitfire's development and had assumed leadership of the design team after Mitchell's death from cancer at age 42. Smith lacked Mitchell's public recognition, but possessed a methodical engineering mind that excelled at solving specific technical problems. Where Mitchell had created the Spitfire's fundamental form, Smith refined that form to meet evolving combat requirements. He had overseen the development of nearly every variant from the Mark I through the Mark 21, each iteration addressing specific operational needs identified by squadrons in combat. The introduction of the Rolls-Royce Griffon engine in 1942 promised significant performance improvements. The Griffon displaced 2,050 cubic inches compared to the Merlin's 1,649 cubic inches. It produced 2,035 horsepower in its most powerful variants, more than 600 horsepower beyond what any Merlin could generate. This additional power should have translated directly into higher speeds and better climb rates. In practice, the Griffon created as many problems as it solved. The increased torque made the aircraft significantly more difficult to handle, particularly during takeoff and landing when pilots needed to apply full power. Several accidents during early Griffon Spitfire trials could be traced directly to torque-induced control problems. British aeronautical engineers had studied contra-rotating propellers throughout the 1930s, recognizing their theoretical advantages. The Royal Aircraft Establishment at Farnborough had conducted wind tunnel tests, demonstrating that contra-rotating propellers could increase propulsive efficiency by up to 6% compared to single propellers of equivalent diameter. The torque cancellation effect was mathematically certain, but translating theory into functioning hardware presented enormous challenges. A contra-rotating system required two separate propeller shafts rotating in opposite directions, complex gearing to drive both shafts from a single engine output, and precise manufacturing to ensure the propellers remained aligned and balanced under the enormous stresses of high-speed flight. Rolls-Royce began developing a contra-rotating propeller system for the Griffon in late 1942. The engineering team, led by Arthur Rubbra, designed a system using two concentric drive shafts. The inner shaft drove the forward propeller through a reduction gear, while the outer hollow shaft drove the rear propeller through a separate gear train rotating in the opposite direction. Each propeller consisted of 4 blades constructed from compressed laminated wood, spruce and birch layers bonded with synthetic resin adhesives. The forward propeller measured 10 feet 5 inches in diameter. The rear propeller, positioned 13 inches behind the forward unit, measured 10 feet 1 inch in diameter. The slight diameter difference prevented the blade tips from striking each other during operation, while maximizing the swept area for both propeller discs. The mechanical complexity was considerable. The gear reduction system added approximately 180 pounds to the power plant's weight. The dual propeller assembly itself weighed significantly more than a conventional single propeller of comparable diameter. Engineers calculated that the contra-rotating system added roughly 300 pounds to the aircraft's empty weight, concentrated in the nose section where it affected the center of gravity and required careful ballast adjustments. Manufacturing precision requirements were extreme. The propeller shafts had to maintain alignment within tolerances of a few thousandths of an inch, while rotating at speeds exceeding 1,200 revolutions per minute and handling torque loads sufficient to drive an 8-ton aircraft to over 400 miles per hour. The strategic situation in 1944 demanded every possible advantage in fighter performance. Allied air forces had achieved air superiority over Western Europe following the Normandy invasion in June, but this superiority came at continued cost. German fighter production had actually increased during 1944 despite sustained Allied bombing campaigns. The Luftwaffe fielded approximately 39,000 fighters during 1944, more than in any previous year of the war. These aircraft, though increasingly flown by poorly trained pilots and constrained by fuel shortages, remained technologically formidable. The Focke-Wulf 190 Dora 9, introduced in the autumn of 1944, represented the culmination of German piston-engine fighter design. Powered by a Junkers Jumo 213 inline engine producing 1,776 horsepower, the Dora 9 could reach 440 miles per hour at 21,325 feet. Its rate of climb exceeded 3,000 feet per minute. More importantly, it maintained excellent performance at high altitudes where Allied bombers operated, making it a serious threat to daylight bombing missions that formed the core of Allied strategic air operations. British fighter squadrons flying escort missions needed aircraft that could match or exceed German fighters in speed and climb rate while maintaining the maneuverability that had characterized the Spitfire since its introduction. The standard Spitfire Mark 9, still equipping many squadrons in 1944, could reach 408 miles per hour at 25,000 feet. This was adequate against most Luftwaffe fighters, but left little margin for tactical flexibility. Pilots needed speed reserves for pursuit, for disengagement if outnumbered, and for the sudden acceleration bursts that characterized aerial combat. The Griffon-powered Spitfire, Mark 14, introduced to operational squadrons in February 1944, offered improved performance with a maximum speed of 446 miles per hour at 26,000 feet. But the torque problems remained severe. Several squadron commanders reported that inexperienced pilots found the Mark 14 genuinely dangerous during ground handling and takeoff. The aircraft wanted to swing violently to the left during the takeoff roll, requiring immediate and aggressive right rudder input to maintain directional control. In combat, particularly during high G turns at full power, pilots had to constantly fight the torque effect, diverting attention from tactical decisions and target tracking. Joe Smith's team recognized that contra-rotating propellers could eliminate these handling difficulties while potentially pushing maximum speed beyond 450 miles per hour. The 6% efficiency gain predicted by wind tunnel tests, combined with the elimination of torque-induced drag from the fuselage and vertical stabilizer flying at constant slip angles to counteract propeller rotation, suggested meaningful performance improvements were achievable. More importantly, the aircraft would be easier to fly. Pilots could focus on combat tactics rather than fighting their own aircraft's tendency to roll and yaw under power. Less experienced pilots, increasingly common as the war continued and attrition claimed veteran aircrews, would be able to extract the Griffon engine's full performance without the constant risk of losing control. The first contra-rotating Spitfire, designated Mark 20 with serial number DP845, was completed at Supermarine's facility in Castle Bromwich in March 1945. The aircraft appeared outwardly similar to standard Griffon Spitfires, except for the distinctive thick propeller spinner housing the dual propeller mechanism and the modified cowling required to accommodate the Rolls-Royce Griffon 61 engine with its contra-rotating drive system. The paint scheme was standard fighter camouflage, dark green and ocean grey upper surfaces with medium sea grey undersides, but the aircraft carried no squadron markings. This was an experimental test bed, intended for evaluation flights under controlled conditions before any decision about production or squadron deployment. Jeffrey Quill conducted the first flight of DP845 on April 12, 1945, departing from Worthy Down at 10:15 hours. The aircraft weighed 8,200 pounds at takeoff, approximately 300 pounds heavier than a standard Griffon Spitfire due to the contra-rotating propeller system. Quill had reviewed the test protocol extensively with Smith's engineering team the previous evening. The flight plan called for a gradual exploration of the aircraft's flight envelope, beginning with basic handling characteristics at low speeds and progressively advancing to high-speed runs at altitude if the initial phases revealed no significant problems. The Rolls-Royce Griffon 61 engine in DP845 produced 2,035 horsepower at 3,000 revolutions per minute using 150-octane fuel. The contra-rotating propeller system consisted of two four-bladed units, the forward propeller rotating clockwise when viewed from the cockpit, the rear propeller rotating counterclockwise. Each propeller blade measured 5 feet 2.5 inches from hub to tip on the forward unit, 5 feet and half an inch on the rear unit. The blades were constructed from compressed laminated wood rather than metal, a manufacturing choice driven by Britain's limited aluminum supplies and the proven durability of wooden propellers under combat conditions. De Havilland had supplied the propellers, drawing on their extensive experience manufacturing wooden propeller blades for bombers and transport aircraft. The gear reduction system connecting the engine output shaft to the dual propeller shafts represented the most complex mechanical element of the entire assembly. Rolls-Royce engineers had designed a planetary gear arrangement where the engine's power divided between an inner solid shaft and an outer hollow shaft, rotating in opposite directions. The gear ratio reduced the engine's 3,000 revolutions per minute output to approximately 1,200 revolutions per minute at the propeller hubs, a reduction necessary to keep propeller blade tip speeds below the speed of sound, where efficiency dropped dramatically and noise levels became unacceptable. The entire gear assembly had to function continuously under loads, exceeding 3,000 foot-pounds of torque, while maintaining precise alignment between the counter-rotating shafts. Manufacturing these components required machining tolerances far tighter than those used in conventional propeller systems. The bearing surfaces supporting the rotating shafts had to maintain clearances measured in thousandths of an inch, while operating at temperatures approaching 200 degrees Fahrenheit from friction and proximity to the engine. Any misalignment would cause vibration, which at high rotational speeds could rapidly escalate into catastrophic mechanical failure. Rolls-Royce had conducted extensive ground testing of the contra-rotating gear system, running prototype units on test stands for hundreds of hours to verify reliability. Several early prototypes had failed during testing, their gear teeth stripped or bearings seized, requiring redesigns before the system was approved for installation in an actual aircraft. The contra-rotating system's weight penalty concentrated mass in the aircraft's nose, shifting the center of gravity forward by approximately 2 inches compared to a standard single-propeller Spitfire. This shift required adding ballast to the tail section to maintain proper weight distribution. Engineers installed lead weights totaling 48 pounds in the fuselage aft of the cockpit, bringing the center of gravity back to acceptable limits. Even with this compensation, DP-845 handled differently during ground operations than conventional Spitfires. The aircraft sat slightly nose down on its landing gear, and the additional weight on the nose wheel required careful attention during taxiing to avoid overloading the strut. Quill's test card for the first flight specified 23 discrete test points, beginning with taxi tests to evaluate ground handling and braking effectiveness. The notes from Supermarine's chief test pilot, also named Jeffrey Quill, he had been with the company since 1936 and had more experience in Spitfires than perhaps any pilot alive, emphasized particular attention to engine cooling during ground operations. The contra-rotating propeller system moved more air through the radiator intakes than a single propeller, but the increased power output and mechanical complexity of the gear reduction system generated more heat. Engineers were uncertain whether the cooling system would prove adequate during extended ground operations or prolonged climbs at high power settings. The cockpit instrumentation in DP-845 included standard Spitfire flight instruments, plus additional gauges, monitoring the contra-rotating propeller system. A dual tachometer displayed the rotational speed of both propellers independently, allowing the pilot to verify they remained synchronized. A propeller pitch indicator showed the blade angle for both units. An oil pressure gauge specific to the propeller reduction gear system provided warning of lubrication problems that could lead to catastrophic mechanical failure. These additional instruments crowded an already dense instrument panel, and Quill had spent time the previous day, familiarizing himself with their locations and normal operating ranges. The flight test engineer, who would monitor the flight from the ground, recording observations and coordinating with Quill via radio, was Maurice Summers, who had worked on Spitfire development since the prototype's first flight. Summers had prepared a detailed observation checklist, focusing on external signs of mechanical stress or failure, unusual vibrations visible in the propeller assembly, smoke or fluid leaks from the cowling, and any asymmetric behavior between the two propellers. A photographer was positioned near the runway to document the takeoff and landing, providing visual records that could be analyzed if problems emerged during flight. Quill advanced the throttle smoothly during the takeoff roll, expecting the familiar left-turning tendency that characterized every Spitfire he had flown. The Griffon engine's rotation created a powerful gyroscopic effect and asymmetric propeller thrust that required immediate right rudder input to maintain directional control. Every Spitfire pilot learned this as fundamental muscle memory during initial training. The aircraft wanted to swing left, and you prevented it by pushing hard on the right rudder pedal while simultaneously advancing the throttle. The correction became instinctive after a few flights, but it remained necessary on every single takeoff. DP-845 accelerated down Worthy Down's grass runway without swinging. The aircraft tracked straight as if running on rails. Quill's right foot hovered over the rudder pedal, prepared to make the correction he had made thousands of times before. The correction was not necessary. The contra-rotating propellers cancelled their torque effects exactly as the engineering calculations had predicted. At 55 miles per hour, Quill eased back on the control column and the aircraft lifted smoothly into the air. The climb was straight and stable. There was no tendency to roll left. There was no need for rudder trim adjustment. The aircraft simply climbed, directly along its flight path, without the constant pilot inputs that characterized every other high-powered single-engine fighter Quill had flown. He leveled off at 5,000 feet and began basic handling tests, establishing the aircraft's response to control inputs at various speeds and power settings. The ailerons responded crisply, producing predictable roll rates without adverse yaw. The elevator provided smooth pitch control. The rudder, which in conventional Spitfires saw constant use to counteract torque effects, seemed almost unnecessary. Quill could fly the aircraft with feet flat on the floor, using only aileron and elevator inputs, and it maintained perfect coordinated flight. This should not have been possible in a 2,000-horsepower fighter aircraft. Every other aircraft Quill had flown required continuous rudder work to compensate for propeller effects. DP-845 flew as if these effects did not exist. At 20 minutes into the flight, Quill advanced to high-speed testing. He pushed the throttle forward to maximum continuous power and trimmed the aircraft for level flight at 15,000 feet. The airspeed indicator climbed steadily. 300 miles per hour, 350. 400. The aircraft remained stable and controllable throughout the acceleration. Quill noted in his post-flight report that the absence of torque effects made the aircraft significantly easier to fly accurately at high speeds. In a conventional Spitfire at full power, the pilot had to maintain constant pressure on the rudder pedals and make continuous small corrections to hold a precise heading. DP-845 held its heading without input, allowing Quill to focus entirely on monitoring engine instruments and airspeed. Second CTA. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The maximum speed achieved during that first flight was 426 miles per hour at 15,000 feet, limited by the test protocol rather than the aircraft's capabilities. Quill was under instructions not to exceed certain speed and G-load limits until engineers had reviewed data from the initial flights and confirmed the propeller system's structural integrity. But even this limited speed run demonstrated performance superior to any production Spitfire variant. The standard Mark 14, powered by the same Griffon 61 engine but with a conventional single propeller, achieved 408 miles per hour at 15,000 feet. DP-845 was 18 miles per hour faster at the same altitude and power setting, a difference attributable to improved propulsive efficiency and the elimination of drag penalties associated with flying in a constant slip condition to counteract torque. Quill conducted several stall tests to evaluate low-speed handling characteristics. The aircraft stalled cleanly at 68 miles per hour, indicated airspeed with full flaps extended and landing gear down, approximately 3 miles per hour lower than a conventional Mark 14 under identical conditions. The stall behavior was benign, with no wing drop or tendency to snap into a spin. Recovery required simply releasing back pressure on the control column and allowing the nose to drop naturally as airspeed increased. This predictable stall behavior was particularly significant because torque effects in conventional high-powered fighters often caused asymmetric stalls where one wing dropped violently, potentially leading to an inverted spin if the pilot did not react immediately and correctly. After 45 minutes aloft, Quill returned to Worthy Down for landing. The approach was stable and required no unusual techniques. The aircraft touched down at 72 miles per hour with full flaps, rolled straight along the grass runway, and stopped within normal distances. Quill taxied to the apron where Smith's engineering team waited, shut down the engine, and climbed out of the cockpit. His first comment to Maurice Summers, recorded in Summers' notes from that day, was direct: "It flies like it's on rails. No torque reaction whatsoever. This is how a powerful single-engine fighter ought to behave." The engineering team immediately began detailed inspection of the propeller system, looking for any signs of stress, wear, or mechanical problems. They found none. The gear reduction system had operated normally throughout the flight. Oil pressure and temperature in the propeller gearbox had remained within expected ranges. The propellers themselves showed no damage or unusual wear on the blade surfaces. The laminated wooden construction had survived the high-speed flight without delamination or cracking. Every mechanical system had functioned as designed. Supermarine and the Royal Air Force conducted an extensive test program with DP-845 over the following 6 weeks, accumulating approximately 40 hours of flight time across multiple test pilots and flight conditions. Each flight explored specific aspects of the aircraft's performance envelope, gradually pushing toward the limits of speed, altitude, and maneuverability. The goal was to gather comprehensive data that would allow Air Ministry officials to make an informed decision about whether contra-rotating propellers should be incorporated into production Spitfire variants or even retrofitted to existing aircraft. On April 25, 1945, test pilot Mike Lithgow flew DP-845 in a series of maximum speed trials at various altitudes. Lithgow was an experienced test pilot who had joined Supermarine in 1943 and specialized in high-speed testing. The trials that day achieved remarkable results. At 21,000 feet with the engine operating at maximum, continuous power, 2,035 horsepower, at 3,000 revolutions per minute, DP-845 reached 444 miles per hour in level flight. This was measured using carefully calibrated airspeed indicators and confirmed by ground-based observers, with theodolites tracking the aircraft's position over measured distances. For comparison, the fastest production Spitfire variant in operational service at that time was the Mark 14, which achieved a maximum level speed of 446 miles per hour at 26,000 feet. DP-845 was matching this speed at a lower altitude, where air density was higher and drag penalties were greater. More significantly, the contra-rotating aircraft achieved its maximum speed with less pilot workload. Lithgow reported that he could maintain maximum speed flight for extended periods without fatigue because the aircraft did not require constant control inputs to counteract torque effects. The climb performance data proved equally impressive. DP-845 could climb from sea level to 20,000 feet in 4 minutes and 51 seconds at maximum power. The standard Mark 14 required 5 minutes and 12 seconds for the same climb. The 21-second difference represented a 4% improvement in climb rate, significant in combat situations where altitude often determined tactical advantage. The improved climb performance resulted from 2 factors: the propulsive efficiency gain from contra-rotating propellers, and the elimination of energy losses associated with flying in uncoordinated flight during climbs, when torque effects were most pronounced. Test pilots evaluated combat maneuverability during a series of flights in early May 1945. Squadron leader James Rankin, a combat veteran with 11 confirmed victories flying Spitfires during the Battle of Britain and subsequent operations, flew DP-845 in simulated dogfighting scenarios against a standard Spitfire Mark 14. Rankin's report, filed with the Air Fighting Development Unit on May 8, provided detailed observations about the aircraft's handling during high-G maneuvers, rolls, and rapid direction changes. Rankin noted that the contra-rotating propellers provided a significant advantage during sustained turning engagements. In a conventional Spitfire at high power settings during a hard turn, the pilot had to apply substantial rudder input to prevent the aircraft from yawing out of the turn due to torque effects. This rudder input created additional drag and required careful coordination with aileron and elevator to maintain optimal turn performance. DP-845 required no such compensation. The pilot could focus entirely on achieving the maximum sustainable G-load and maintaining proper angle of attack without fighting secondary effects from the propeller. Rankin estimated this reduced pilot workload by approximately inter-pilot PERS, 30% during intensive combat maneuvering. The aircraft's roll rate was exceptional. Lithgow measured roll performance during dedicated tests on May 3, using a stopwatch to time rolls through complete 360-degree rotations at various speeds. At 250 miles per hour indicated airspeed, DP-845 achieved a full roll in 1.3 seconds. The standard Mark 14 required 1.6 seconds for the same maneuver. This 0.3 of a second advantage might seem minor, but in air combat, where success often depended on achieving firing position fractions of a second before an opponent, the improvement was tactically significant. Engine cooling, which had been a concern during initial design reviews, proved adequate under all tested conditions. The contra-rotating propellers moved sufficient air through the radiator and oil cooler intakes to maintain acceptable temperatures, even during prolonged full-power operations. The Griffon 61 engine's coolant temperature stabilized at approximately 215 degrees Fahrenheit during sustained climbs, well within the acceptable operating range. Oil temperature remained below 200 degrees Fahrenheit, except during ground operations on hot days, where it occasionally approached the maximum allowable limit of 210 degrees. The mechanical reliability of the contra-rotating gear system exceeded initial expectations. After 40 hours of flight testing, engineers disassembled the propeller reduction gearbox for detailed inspection. They found minimal wear on gear teeth, no evidence of bearing distress, and normal oil condition without metallic contamination that would indicate component degradation. The wooden propeller blades showed no delamination or structural problems. The system appeared capable of sustained operational use without extraordinary maintenance requirements. However, maintenance complexity presented a different picture when ground crews attempted routine servicing procedures. Changing a damaged propeller blade on a conventional Spitfire required approximately 2 hours of work by a 3-man crew with standard tools. The same procedure on DP-845 required 6 hours and specialized equipment to access the rear propeller assembly. The contra-rotating system's mechanical complexity meant that any repair or adjustment to the propeller mechanisms demanded more time, more skilled labor, and more specialized tools than conventional systems. This maintenance burden would prove significant in the calculations about whether to proceed with production. By mid-May 1945, the strategic context that had driven the development of DP-845 had fundamentally changed. Germany surrendered unconditionally on May 8, ending the war in Europe. The immediate operational need for improved fighter performance against the Luftwaffe disappeared overnight. Air Ministry priorities shifted abruptly from offensive operations over occupied Europe to supporting the continuing war against Japan and planning for post-war force structure. The contra-rotating Spitfire, which had been conceived as a solution to specific combat challenges in the European theatre, suddenly found itself a technology without a clear mission. Joe Smith's engineering team compiled comprehensive test results into a formal report submitted to the Air Ministry on May 23, 1945. The report documented the performance advantages in meticulous detail. The 18-mile-per-hour speed increase at 15,000 feet, the 4% improvement in climb rate, the enhanced handling characteristics that reduced pilot workload during combat maneuvering, and the complete elimination of torque-induced control difficulties. Every measured parameter showed the contra-rotating system delivered meaningful performance benefits. The report also acknowledged the disadvantages: the 300-pound weight penalty, the increased manufacturing complexity, the substantially higher maintenance requirements, and the need for specialized training for ground crews. The Air Ministry's response arrived on June 14, 1945. Officials acknowledged the impressive test results but declined to authorize production of contra-rotating Spitfires or retrofitting of existing aircraft. The decision memorandum, preserved in British National Archives files, cited several factors. Manufacturing capacity previously dedicated to fighter production was being redirected toward bomber and transport aircraft needed for Pacific operations and post-war requirements. The improved performance, while significant, was not sufficient to justify the additional cost and complexity when measured against operational needs in the Pacific theatre, where Japanese fighters were generally less capable than the German aircraft for which the contra-rotating system had been optimized. Most significantly, the memorandum noted that jet-powered fighters were entering squadron service and would soon replace piston-engine aircraft entirely, making further investment in piston-engine fighter development inadvisable, regardless of performance benefits. This last point reflected a broader strategic reality that had been developing throughout 1944 and 45. The Gloucester Meteor, Britain's first operational jet fighter, had entered squadron service with the Royal Air Force in July 1944. Though the early Meteors were limited to air defence duties in Britain due to concerns about the technology falling into German hands, their performance demonstrated that jet propulsion represented a fundamental advance beyond anything achievable with piston engines and propellers, contra-rotating or otherwise. The Meteor could exceed 400 miles per hour in level flight with its early engines, and development work was already underway on more powerful turbojets that would push speeds well beyond 500 miles per hour. Jeffrey Quill, in a letter to Joe Smith dated June 20, 1945, expressed frustration with the Air Ministry's decision. Quill argued that the contra-rotating Spitfire represented the fullest realization of the aircraft's potential and deserved production, even if only in limited numbers for specialized squadrons. He noted that jet fighters, despite their speed advantages, had significant limitations, including high fuel consumption, limited range, and immature technology that caused frequent mechanical problems. A fully developed contra-rotating Spitfire could serve as a highly capable fighter for situations where jet aircraft were impractical. Smith's response, written 2 days later, acknowledged Quill's points, but concluded that the decision was final. The era of piston-engine fighter development had effectively ended, and continued work on contra-rotating propellers would consume resources, better directed toward jet aircraft and other post-war priorities. DP-845 continued flying through the summer of 1945, participating in occasional demonstration flights and serving as a testbed for propeller research unrelated to military applications. The aircraft accumulated approximately 60 total flight hours before being retired from active testing in September 1945. It was subsequently used for ground instruction at a Royal Air Force technical training facility where student mechanics could study the contra-rotating propeller system and learn the specialized maintenance procedures it required. By 1948, the aircraft had been scrapped, its components recycled or disposed of, according to standard procedures for obsolete military equipment. The contra-rotating propeller technology itself did not disappear. Several post-war aircraft designs incorporated contra-rotating propellers, recognizing the performance benefits Smith's team had documented. The Soviet Union's Tupolev Tu-95 strategic bomber, which first flew in 1952 and remained in service into the 21st century, used contra-rotating propellers on all four engines. The system's advantages in reducing torque effects and improving propulsive efficiency proved particularly valuable for large aircraft, where engine power exceeded 10,000 horsepower and conventional propellers reached the limits of what a single propeller disc could absorb. Various naval patrol aircraft and transport planes adopted contra-rotating systems when their missions required maximum efficiency and range rather than minimum complexity. But for fighter aircraft, the technology arrived too late. Jet propulsion rendered the entire question of propeller optimization obsolete within 5 years of DP-845's first flight. By 1950, no major air force was developing new piston-engine fighters. The performance advantages that contra-rotating propellers provided, real and measurable as they were, simply did not matter when jet aircraft could fly 100 miles per hour faster and climb twice as quickly, regardless of propeller configuration. The test pilots who flew DP-845 carried memories of the aircraft throughout their subsequent careers, and their reflections provide insight into what the contra-rotating Spitfire represented beyond performance data and engineering specifications. Jeffrey Quill, in his autobiography published in 1983, devoted several pages to his experiences with the contra-rotating variants. He described the aircraft as representing the logical conclusion of piston-engine fighter development, and noted that flying it provided a glimpse of what fighter aircraft could have become had jet propulsion not revolutionized aviation. Quill emphasized the psychological impact of flying an aircraft that eliminated torque effects entirely. He had learned to fly Spitfires in 1936, when the prototype was new and demanding. Every hour he had accumulated in Spitfires since then, thousands of hours, spanning 9 years and dozens of variants, had included the constant awareness of propeller torque and the necessary compensations. Flying DP-845 was different. The aircraft went where he pointed it without requiring continuous subtle corrections. This created what Quill described as a peculiar sensation of directness, where pilot intention translated to aircraft response without intermediate steps. He suggested that if contra-rotating Spitfires had been available in 1940 during the Battle of Britain, they would have provided tactical advantages, particularly for less experienced pilots who struggled with torque management during high-stress combat. Mike Lithgow, in interviews conducted decades after the war, recalled the contra-rotating Spitfire as the finest handling aircraft he had flown during his entire career as a test pilot. Lithgow had flown hundreds of different aircraft types, including early jets, experimental designs, and various production fighters from multiple nations. He maintained that DP-845 possessed handling qualities superior to any contemporary piston-engine fighter he had tested, including American P-51 Mustangs and later model Focke-Wulf 190Ds captured after the war. The absence of torque effects, combined with the Spitfire's fundamentally sound aerodynamic design, created an aircraft that responded precisely to pilot inputs across its entire speed range. James Rankin, the combat veteran who evaluated DP-845's fighter capabilities, provided a tactical perspective in his official report and in later correspondence. Rankin noted that the reduced pilot workload during combat maneuvering would have significant implications for pilot fatigue during extended missions. Fighter operations in 1944 and 45 often involved flights of 3 to 4 hours duration, escorting bombers deep into German territory and engaging enemy fighters throughout the mission. The physical and mental effort required to fly a high-powered fighter accurately for such periods was substantial. Rankin estimated that flying a contra-rotating Spitfire would reduce pilot fatigue by approximately 25% during typical escort missions, allowing pilots to maintain peak alertness and reaction times longer into the flight. However, Rankin also acknowledged that the performance advantages, while real, would not have changed fundamental tactical realities in air combat. Success in fighter engagements depended primarily on situational awareness, tactical positioning, teamwork, and pilot skill, rather than small differences in maximum speed or climb rate. An 18-mile-per-hour speed advantage might occasionally allow pursuit of an otherwise elusive target or escape from an unfavorable engagement, but these situations were less common than popular imagination suggested. Most combat occurred at speeds well below maximum, where maneuverability and energy management mattered more than absolute top speed. The contra-rotating Spitfire's main advantage was not making marginally faster aircraft, but making the same aircraft easier to fly well under demanding conditions. The ground crews who maintained DP-845 during its testing phase provided a different perspective entirely. Sergeant Thomas Wickham, a senior aircraft mechanic who worked on the contra-rotating Spitfire at Worthy Down, recorded his experiences in a diary that was later donated to the Imperial War Museum. Wickham's entries from April and May 1945 document the practical challenges of maintaining the complex propeller system. He noted that routine inspections took twice as long as on standard Spitfires because the contra-rotating mechanism required checking multiple additional components. Any work on the rear propeller required first removing the forward propeller, a time-consuming process that demanded careful attention to avoid damaging the wooden blades or disturbing the precisely balanced assembly. Wickham's diary included a telling entry from May 12, 1945, after he and his crew had spent an entire day replacing a damaged blade on the rear propeller. The blade had been struck by a stone thrown up during a landing on a rough airfield, causing a small crack in the laminated wood structure that required replacement. On a conventional Spitfire, this repair would have taken perhaps 3 hours. On DP-845, it consumed 9 hours of labor from 3 skilled mechanics using specialized tools. Wickham wrote, "Fine aircraft to fly, they tell me, but a bugger to fix. Give me a standard Mark 14 any day. At least when something breaks, I can get it sorted before tea time." This maintenance burden, documented in detail by Wickham and other ground crew personnel, represented a significant practical limitation that the Air Ministry's decision memorandum had correctly identified. Modern air forces required not just capable aircraft, but aircraft that could be maintained by reasonably trained personnel using available tools and facilities. The contra-rotating Spitfire demanded specialized knowledge and equipment that would have complicated logistics and reduced operational availability rates in squadron service. The story of the contra-rotating Spitfire represents a particular moment in aviation history when engineering excellence collided with strategic obsolescence. The aircraft was genuinely superior to conventional Spitfires in measurable ways. The test data was unambiguous. Pilots who flew it universally praised its handling characteristics, yet it was never produced in numbers, never saw combat, and ultimately had no influence on the war's outcome or on subsequent fighter development. This outcome was not a failure of engineering or testing, but a consequence of technological transition occurring faster than incremental improvements could matter. Similar patterns appeared throughout the final years of World War II, as multiple nations pushed existing technologies toward theoretical limits, while newer technologies rendered those improvements irrelevant. Germany developed the Tiger II heavy tank with its 88mm gun and thick armor, an extraordinary vehicle that represented the peak of conventional tank design. But the Tiger II was complex, expensive, and difficult to maintain, while Allied forces simply produced overwhelming numbers of adequate tanks, like the Sherman and Soviet 34. Germany's sophisticated weapons arrived too late, in too few numbers, at too high a cost to affect outcomes determined by industrial capacity rather than technical sophistication. Japan's attempts to develop improved versions of the Zero fighter followed a similar trajectory. Engineers created variants with more powerful engines and better armament, but these improvements could not close the gap created by American fighters designed from newer baseline assumptions. The Japanese aircraft industry struggled to produce thousands of improved Zeros, while American factories produced tens of thousands of Hellcats, Corsairs, and Mustangs that incorporated fundamental advantages in engine power, structural strength, and systems integration. The contra-rotating Spitfire occupied this same category of technical achievements that arrived at the wrong moment in history. If the system had been ready for production in 1942 or 43, it might have equipped squadrons and influenced combat outcomes over Europe. If jet propulsion had developed more slowly, contra-rotating piston fighters might have served through the late 1940s. But the actual timing meant the technology was perfected just as it ceased to matter. The test flights in April and May 1945 demonstrated what piston-engine fighters could achieve at their absolute limit. 2 months later, that limit was no longer relevant to military planning. Joe Smith continued as Supermarine's chief designer through the transition to jet aircraft, leading the development of the Supermarine Swift and other post-war designs. He never again worked on propeller development. The institutional knowledge his team had accumulated about contra-rotating systems was documented in reports and then largely abandoned as the company focused entirely on jet propulsion. Smith retired in 1956, having overseen Supermarine's complete transformation from the company that built the Spitfire to a jet aircraft manufacturer. In interviews late in his life, he expressed pride in the contra-rotating Spitfire as a technical achievement, but acknowledged it had been, in his words, a solution perfected just as the problem disappeared. Jeffrey Quill remained with Supermarine as chief test pilot through 1954. Flying the company's jet fighters and contributing to their development. He never flew another aircraft that handled quite like DP-845. The sensation of flying a powerful single-engine fighter without torque effects remained unique to that specific aircraft and the handful of other contra-rotating prototypes tested in the immediate post-war period. Quill's autobiography, published nearly 4 decades after that first flight in April 1945, concluded its chapter on the contra-rotating Spitfire with a simple observation. It was the best Spitfire I ever flew, and the least necessary. That assessment captured the essential irony of DP-845's story. The aircraft represented genuine innovation, solving real problems through clever engineering and careful development. The performance improvements were not theoretical but measured and verified. The handling advantages were not subjective impressions, but consistent observations across multiple, experienced test pilots. Everything about the aircraft validated the design team's goals and demonstrated that contra-rotating propellers delivered their promised benefits. And none of it mattered because the world had moved on to jet propulsion. The morning of April 12, 1945, when Quill first took off in the contra-rotating Spitfire, and felt the aircraft track straight down the runway without torque reaction, represented both a triumph and an ending. The triumph was proving that engineering could eliminate fundamental limitations that had constrained piston-engine fighter performance since aviation's beginning. The ending was the quiet realization that this triumph arrived too late to influence anything beyond technical journals and test reports. The aircraft flew beautifully, handled precisely, and demonstrated measurable superiority over conventional designs. It simply did so at the exact moment when beautiful handling and measurable superiority in piston-engine fighters ceased to determine the future of military aviation. DP-845 existed as proof that incremental improvement, no matter how well executed, cannot compete with fundamental technological change. The contra-rotating propellers worked exactly as designed. The aircraft performed exactly as predicted, and the world moved on to jets, leaving the finest piston-engine fighter ever developed as a footnote, a curious might have been, and a reminder that timing matters as much as technical excellence in determining which innovations shape history and which simply demonstrate what could have been achieved had circumstances been different. The aircraft was scrapped in 1948. No examples survived. No photographs exist of it in flight. Only a few grainy images of it parked on the tarmac at Worthy Down. The detailed test reports reside in archives, occasionally consulted by aviation historians studying propeller development or Spitfire variants. The contra-rotating Spitfire achieved everything its designers intended, except the one thing that would have mattered. arriving at a moment when its capabilities would have changed outcomes rather than simply documenting possibilities. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.